I wonder what's on TV today. Let's look.
Hello, everybody. Today we've got some fabulous magnets for you, which we are crazy excited about.
Well, Mitchell, I would say that the magnet is really the Kim Kardashian of the physics world because they're all about attractive and repulsive forces. You see that the magnetic force is always perpendicular to its direction of velocity.
Are you saying that the force exerts no work? If that's true, then the magnet is able to gain a centripetal acceleration and move in a circle. That's amazing!
Yes, Mitchell, there's no work exerted. And that's not all. The strongest points of a magnetic field, the poles, are located on the ends of a magnet. They affect one another by attracting and repelling each other depending on their charge. Like charges repel, and opposite charges attract.
Unbelievable! Did you know that the Earth's magnetic south pole is actually located at the north pole of the
Really?
Earth? That's how powerful magnets are.
Well, I'll tell you this, Mitchell. All magnetic fields have field lines that are invisible to the human eye. They fill the space where a magnet has the ability to attract or repel other magnets.
Well, that is truly outstanding. And don't forget that you can buy the magnet for just $34.94. $34.94.
Wow.
Now, Leah, can you tell me any other properties of the magnet?
Well, Mitchell, you might not know this, but magnetic fields actually have a lot of strength, which are measured in the metric unit Teslas, represented by a T. To get the general idea, a refrigerator magnet is about 1,000 Tesla.
Oh, but wait, there's more. A magnetic field around a current-carrying wire depends on the relative orientation of the B field of the wire and the current in the wire. Magnetic force is exerted when the wire is oriented perpendicular to the B field and gets stronger the larger the angle, up to 90 degrees.
To determine the direction of the magnetic force, you can use the right-hand rule.
Exactly. You can do that by holding your right hand out like this and orient your hand so that the fingers move in the direction of the B field and your thumb in the direction of the current. The direction your palm faces is the direction of the magnetic force on the current.
That's correct. Yes, and the main factor that directly affects the strength of an electromagnet is current, and there are more ways to change the strength of an electromagnet, but that is because those factors change the current.
For example, number of coils or loops in the wire, adding batteries or voltage, and the size of the wire will increase the strength of the electromagnet.
Now tell me, Mitchell, are there any other uses for the magnet?
Yes, Leah. In fact, electromagnetic induction is when a conductor is placed in a charging magnetic field which produces voltage, and the current is known as an induced current.
So you can actually make your own voltage. I know that Michael Faraday discovered this and came up with the law of electromagnetic induction, a law that predicts how a magnetic field in an electric circuit will produce an EMF.
I don't need to work it out to know it's a bargain. And you can also use magnets to create awesome things, like maglev trains that work using magnetic levitation so that they can travel high speeds without friction.
Call the number on the bottom of your screen if you'd like to buy the magnet. For today's special value price of just $34.94. Only $34.94.
Wow.
What in the world was that?
Welcome to another episode of Man vs. Wild.
Light is quite an interesting thing. It can act as a wave, particle, or both depending on the situation. It is widely accepted that light is made out of photons, which are the tiny fundamental particles of light. Light can also do a bunch of crazy things, as you will soon see.
As you can see here, we found a pond in the wild. One really cool thing that you can do with light is if you stick an object in the water, you can see the refraction of the object. You see how it looks like two pieces? It's so cool, right? Water can also reflect light, right? It's like when you're looking in a mirror and like you see yourself. It's so cool. Light can also do this neat thing called diffraction, diffraction. And it's like when light bends around things. One example of that is like if you look at the clouds, sometimes there's like a silver lining around them. That's an example of diffraction. The last really cool thing light can do is called interference. It's like if you put two flashlights shining right at you, it looks way brighter than one flashlight. That's constructive interference, right? Because the light waves combine and they make it really bright. And then there's also destructive, which is like when they make it dark.
Light and sound waves have many similarities, such as being able to carry energy, be refracted and diffracted, but that's about where the similarities end. Light is a transverse wave and can travel with or without a medium, but sound is a longitudinal wave and must have a medium to travel through. Light waves also travel about 882,000 times as fast as sound. Light travels about 300 million meters per second in a vacuum.
The last thing I'll show you today before I settle down for the night is how to solve for velocity, wavelength, and frequency and period of a wave using the wave speed equation. So it's a very simple equation. All you have to do is say velocity equals wavelength times frequency. So it's really easy. So if you want to solve for velocity, you just multiply wavelength and frequency. But let's say you want to solve for something like wavelength. Well, then you just divide the velocity by the frequency, and vice versa if you want to solve for frequency. So if you want to find frequency, you just multiply the velocity by the wavelength, right? Okay, so then this is where it gets really interesting. Then you can solve for the frequency. So all you have to do to find the frequency of a wave is divide the speed of light by the wavelength. So all you have to do, just give me a second. So if you're gonna do green light, which has a wavelength of 510 nanometers, then all you have to do, give me a second to think. So if you have light with 510 nanometers, which is like green, then it's going to equal 5.88 times 10 to the 14th. That's a lot of times. It goes like this, am I right? And then all you have to do from there, I mean, you've done the hard working from there. All you have to do to find the period is do 1 divided by the frequency, and that will give you your period. All right, I've had enough for today. I'll see you next time on Man vs. Wild.
What?
Oh my gosh, it's finally done. My time machine. Where should I go? Should I go to ancient India? Should I go to the jungles of Egypt? I don't know.
No, I said you should go to the future.
Wait, what did you just say?
I said you should go to the future.
No, before that.
No, Einstein?
Einstein. I should visit Einstein. I say go in here, set a date, and we should be all ready to go. Ready? It worked!
Why, what in the world? Who are you?
Oh my gosh, Einstein, it's an honor to meet you. I'm a journalist from the New York Times. What have you been working on?
Well, I've recently developed a formula that explains the relationship between mass and energy. E equals mc squared. In other words, its energy is equal to mass times the speed of light squared. Using this equation, I can tell you the exact amount of kinetic energy present in a given amount of mass. So for example, if you were to take a mass of 1 kg, I can find its kinetic energy by simply plugging it into the equation. So we would take the mass of 1 and multiply it by the speed of light squared, which comes out to be 9 times 10 to the 16 meters squared seconds to the power of negative 2, resulting in 9 times 10 to the 16 joules of kinetic energy.
Wow, that's really cool stuff. What else?
You see, my boy, physics is all around us. There are all kinds of forces acting in nature. Specifically, there are 4 fundamental forces in decreasing order. In decreasing order, it goes the strong force, the electromagnetic force, the weak force, and the gravitational force. The strong force is responsible for the binding of nuclei. The electromagnetic force is responsible for the binding and repulsion of charged particles. The weak force is responsible for the decay of particles. The gravitational force is what keeps us on the ground. It's gravity. You know gravity, right?
Well, yes, of course. I'm not stupid. I even know some things you don't know.
Oh, really? Like what?
Well, do you know what an MRI is, or what a CAT scan is, or how an aurora borealis works?
Explain, explain.
Well, an MRI is a magnetic resonance imaging and can find tissue and tendon energies. A CAT scan is computerized tomography that provides a detailed image of injuries to bones by use of X-ray imaging. An aurora borealis is caused by charged particles from the sun colliding and entering the Earth's atmosphere.
Oh, so you think you're so smart. But do you know of Heisenberg's uncertainty principle? I bet you think that it's possible to accurately determine the momentum and position of a particle at one point in time. Well, it isn't.
Whoa, buddy, calm down, okay?
You better watch what you say. I'm the greatest physicist of all time.
Arguably, I think Schrödinger is the greatest physicist of all time. His cat experiment challenged the theory of indeterminacy, a theory that stated that a particle can be in two states at once. Schrödinger disproved this by placing a cat in the opaque box with radioactive material that would possibly, 50% chance, be released, either killing the cat or leaving the cat unharmed. According to quantum mechanics, the cat will be half dead and half alive. This is impossible since the cat will either be alive or dead, not both.
This is ridiculous. You anger me, Jimmy Dean. Go back where you came from.
Good day to you, sir.
Well, did it work? Did you meet Einstein?
Unfortunately.
What has TV come to these days?
Now to our weekly 7-day forecast with Mohammed Khan.
Thanks, Yash. Now for Monday's forecast. Okay, well, I'm just getting word that we have incoming information that coming from our NASA telling us an unexpected supernova has occurred near our planet and is emitting gamma radiation as we speak. We are therefore warning the public to remain safe and avoid gamma radiation exposure. Gamma radiation, if you don't know, has the highest amount of energy and smallest wavelength, which means it has the highest frequency out of all the waves, produced by the hottest, most energetic object in the universe, such as a supernova. Gamma rays are also the most damaging to humans, so stay safe, guys. Moving on to Tuesday. It looks like Tuesday we have clear skies and a whole lot of sun. Remember to put on that sunscreen and protect yourself from those harmful UV rays. Now these ultraviolet rays here, they have shorter wavelengths than visible light and thus have a higher frequency and more energy. There are also three types of UV rays. There is UVA, UVB, and UVC. All these rays are harmful and can cause cancer. UVB rays cause sunburns and has more energy than the UVA. But UVC, however, has the highest amount of energy, but is not in sunlight as the other rays are. So Wednesday, it seems like we're going to be having some light showers until about high noon. However, when that clears up, make sure you keep your eyes out for some rainbows, a phenomenon that occurs when visible light is separated through the water vapor into the atmosphere, which then break apart white light, resulting in light waves of varying length and of different frequencies, with the color red being the longest at 700 nanometers and the color violet being the shortest at 380 nanometers. Okay folks, put away those kites because we're going to be seeing a lot of lightning storms. Fun fact, did you know that it was recently discovered that lightning occurs at such high speeds that X-rays are actually produced? X-rays, as we know, have much higher energy, and much shorter wavelengths, resulting in a higher frequency than ultraviolet light. These rays also are created from objects that are millions of degrees Celsius and have large amounts of electricity, such as said lightning. Alright, finally on to Friday, guys. So Friday looks like we're going to have some clear, sunny skies and an unusually dry evening with little humidity. So, interesting experiment you guys can do. You guys can, it doesn't require any equipment besides your hands. And so today as the sun is setting, you guys should extend your arm over the ground and then turn your hand over back and forth. You'll notice that the ground facing side of your hand feels slightly warmer than the sky facing side. Now the reason for this is that greenhouse gases in the colder atmosphere above you are emitting less infrared radiation downward than the warmer ground is emitting upward. This is one way to better appreciate the fact that the Earth is continuously losing infrared energy to outer space. A little more about infrared energy. It is part of the invisible portion of the EM spectrum and has a lower frequency, therefore longer wavelength than that of UV. A perfect example will be your remote. So Saturday. So looking at our advanced Doppler screen radar here, there seems to be a possibility of a hurricane coming our way. So forgetting dangerous hurricane Wilga for a moment, let's focus on our cutting-edge Doppler screen, which uses microwaves. In case you didn't know, microwaves are extremely high-frequency radio waves that occupy a wide range of the electromagnetic spectrum. Microwaves are also a form of heating your food, as we all know, and they produce heat waves which take up a lot of the electromagnetic spectrum. Okay, so moving on to Sunday. Tracking the progress of Hurricane Wilga, we are just now receiving information via radio that has reached our coast. Our transmission signals, however, are getting disrupted because it seems that the high winds of the hurricanes are interfering with the radio waves. By the way, radio waves have the longest wavelengths on the electromagnetic spectrum and are generated by a transmitter and detected by a receiver. Since this wave has the longest wavelength, consequently it also has the lowest frequency as well as a very low energy. Now before I go, I want to wrap up my segment with the dual nature of light and the photoelectric effect. So first of all, light is a wave, and so that explains why light can bend around an object. But light is also a particle, and is why light can also travel in a straight line, giving it a dual nature. So the photoelectric effect. This is the process of pushing electrons and freeing them from a solid surface. Materials that do this are called photoemissive, and these ejected electrons are called photoelectrons, but are not different than any other kinds of electrons. Back to you, Yash.
Oh, thanks, Mohammed.
Why is everything so physicsy?
Thank you, and welcome to everyone's favorite game show, Physics Trivia. I am the host. Today's contestant, Desiree Barrera and Leah Sato, have just entered our bonus round and are trying to win our grand prize, $30,000 in cash and an all-expense-paid 6-day vacation to Hawaii. Okay, Desiree and Leah, in order to win the grand prize, you must answer more than the others correctly out of 6 bonus questions or given statements. All of the questions are elongated, and you need to really know the thermal energy in order to answer correctly. If not, you go home with our consolation prize, a fine set of encyclopedias on home repairs. Remember, whoever raises their hand first means they will be answering first. If you're correct, you'll go on to the next question. If you're wrong, your challenger has the option to fix it. Are you ready?
I'm ready.
I'm ready.
Okay. First question. How would you explain the kinetic theory of matter to someone who knew nothing about it?
Oh, I got it. It really isn't that hard. It explains that the state of matter is composed of a large number of small particles, which is just individual atoms or molecules that are in constant motion, where they are just colliding and exchanging energy. The particles in a gas are very far apart, and it is mostly empty space, while everything moves freely. The particles in a liquid slip and slide past each other, while they are mostly together. Lastly, in a solid, it is an ordered structure, and the particles are very close together.
Wow, that explanation, you're bound to get it. Next question. Who can tell me what the first and second law of thermodynamics are?
The first law of thermodynamics states that the energy cannot be created or destroyed, so the total quantity of energy in the universe stays the same. The second law states about the quality of energy. It states that the energy is transferred or transformed, and more of it is wasted.
Correct. Now you're tied 1 for 1. Next statement. Explain and let people know of the thermal energy transfers.
So heat can be transferred from one place to another by these 3 methods: conduction in solids, convection of fluids, liquids, or gases, and radiation through anything that will allow radiation to pass. For example, the sun. Sun radiates energy in the form of solar radiation, raising its temperature. As the sun is the emitter, it gives out the heat source. Convection occurs when the warmer areas of a liquid or gas rise to cooler areas in the liquid or gas. A good example of convection is the atmosphere. The Earth's surface is warmed by the sun, and the warm air rises and cool air moves in. Conduction is the transfer of heat between substances that are in direct contact with each other. Metal is a good conductor of heat. It occurs when a substance is heated. Particles will gain more energy and vibrate more, thus continuing.
Wow, y'all's brains are proving to be a pure genius. Next question. Can anyone tell me what thermal equilibrium is?
Oh, easy. It's where 2 objects really don't exchange any heat energy while in contact. They are said to be at the same temperature.
Very good. Glad the simple ones aren't getting to your heads. Now tell me the difference in definition of temperature, heat, and thermal energy.
Wow, that's a bit. Okay, I got it. Actually, I don't really know that question. I feel like they are similar, so I'm not very sure.
Okay, can Leah tell me the answer?
She's right. It's a tough one. Heat is the transfer of energy between 2 objects because of a temperature difference, represented by Q, measured in joules or calories. Temperature is the average kinetic energy, which is measured in Fahrenheit, Celsius, or Kelvin. Thermal energy of a system is a result of a difference in temperatures. Thermal energy of an object is the total amount of random kinetic energy for all the atoms in the object. They all tie in at one point, but have their own little links.
Correct. Now we're 3 for 2. It is the last question. Use an example and tell us about specific heat.
When heat energy is added to a substance, the temperature will change by a certain amount. The relationship between heat energy and temperature is the difference for every material, and the specific heat is the value that describes how they relate. So the equation would be heat energy equals the mass of the substance, specific heat, and change in temperature. So let me think of a good example problem. So the specific heat of gold is 129 joules per kilogram times Kelvin. What is the quantity of the heat energy required to raise the temperature of 100 grams of gold by 50 Kelvin? So if the mass of the gold is 100 grams, we have to convert it to 0.1 kilograms. The heat energy can be found using the formula heat equals 0.1 kilograms times 129 joules over kilograms times K times 50 K. The energy required to raise the temperature of the piece of gold is 645 joules.
Congratulations, Desiree. Pack your bags, and we've got your prize.
Thank
you
you.
were headed to Hawaii. Leah, you did very
I
well.
don't want an encyclopedia!
Better luck next time. Well, folks, this was today's episode of Physics Trivia. Come back next week for some more prizes.
Okay.
Alrighty, class. Today we're going to be learning about the study of lenses and mirrors, which is called optics. Oh, come on. It's not that bad, guys. So to start off, we'll talk about something simple, reflection and refraction.
Have we already learned about that?
Well, you probably know some things about it, but I'm going to explain the science of it. Whenever an object strikes a reflective surface, it always reflects the same angle that it came in at. So you see here, so you came in, got this angle, and it always reflects with the same angle. So, with refraction, the light ray will go in and refract through the object, and then come back out the same angle that it was before. You guys understand that?
Your mom's refraction.
Okay, Mitchell. It's not good to make comments like that in class. The next part of optics has to do with how light rays interact with lenses.
Okay, Four Eyes.
Alrighty. Your glasses, for example, are a form of lens. The kind that gets thinner towards the edges is called a convex lens. And with that, when the convex lens, there's three cases. Go ahead and pass that around so everybody can see. With the first case, an object will be refracted. An object outside of the focal point. It'll be reflected, but it will still be the same size. With the second case, don't do that again, Leah. Watching you.
Mitchell, can I see that picture?
Let me look at it real quick.
I want to know about refraction.
With the second case, the object is at the focal point, and when that happens, no image is created at all. The third case is when the object is inside the focal point. And when that happens, the object or the image appears behind. However, it's a virtual image, so you can't really see it.
What else do we need to know? I'm tired of these lessons.
Well, there's also math to go with it. You guys love math, don't you? Alright, Mitchell. I'd like you to solve this problem here using the thin lens equation.
Is it that equation right there?
Yes, this equation right here. So basically how this works, 1 over the distance of the object plus 1 over the distance of the image equals 1 over the distance of the focal length. So, in that problem there, I give you the focal length and the distance of the object, and you have to solve for the distance of the image.
So if the object distance is 6 centimeters and the focal length distance is 4,
So here's how you would write that.
then it would be -2.
Well, so, wait, you said the object distance was
6.
6 plus 1 over the image distance equals 1 over 4, correct?
Yes.
So, using this, you would subtract that. So you would go minus 1 over 6, and that would give you your image distance, which comes out to,
Oh, it'd be 3/12 minus 2/12. It'd be 1/12. I'm stupid.
that's right, Mitchell. Good job.
Nerd.
Nerd. Hey, wake up!
Alright guys, the last part of this has to do with optic fiber. Do you guys know what optic fiber is used for? Any of you?
No.
What?
Okay, Optic fiber is mainly used for transmitting data. It's even responsible for cable TV. Basically, it's like shooting a beam of light down a bendy hallway made of perfect mirrors. We do this because light travels extremely fast and can be used to relay information very rapidly. Does everybody understand? Sure.
Whatever. Loser.
Excuse you, you leave when I dismiss this.
What kind of TV show is that? I'm done with TV. I cannot believe this.